Hello everyone and welcome to a new episode of All Things Y0da. In today's episode, we're going to talk about the FlareOn challenge, in particular the Yoda reverse engineering challenge done by Mark Lechtig from Mandiant. I don't usually do CTFs. I have done total two. The first one was the Hexrays one and this time the Mandiant one. Usually if I am to do the CTF it's mainly for educational purpose and to illustrate certain things. So in today's video we're not gonna go into the details of all the challenges and how they are solved in details. Instead I'm gonna give the bigger picture and just explain on a higher level how they are solved, but the main goal is for now is to look at the challenge and how it works. In later episodes we can take individual problems from this challenge and discuss them in details. With that, let's get started. First things first, this is the binary. I have totally reverse engineered it. I know it's safe. Normally I would run it in a VM, but since it's safe, I'm just gonna run it locally. So let's take a look really how it looks like. So here it is. This is the challenge when we run it. Now, as it is like this, maybe we can use networking tools to see what port it's listening at and so on. But since it's a reverse engineering challenge, I prefer to go in details and reverse engineer the whole thing and see what comes out of it. So now that we see how it looks when it runs, let's try to disassemble it with Y0da. So let's reverse it. So I'm gonna run Y0da and let it analyze it. And let's see what comes of Y0da just like that out of the box. And here, when we look at start, already what we see is some function chunks. Also, please keep an eye on the navigation here at indicator here, this arrow. So this is the entry point. We can verify that we only have one entry point, so it's just the start. And we have a bunch of function chunks. Fine, let's follow it and see what's this all about, why this is a chunked function. So as we see here, the arrow is here. If we follow that jump, so we have one instruction, then one jump. Let's follow the jump. And now look, it went from this spot here all the way here. And then we only have one instruction again and another jump. So if we follow that jump, it went somewhere else. And same story, one instruction, then another jump, which is here, which is a return instruction. And definitely this is not its own function. So let's delete this. And same here is okay for the function chunk, but this one was not. So if we are to fix this, we have to tell Y0da that this part should belong to start. So if I say edit functions append function tail, we can specify start. And now it seems to be fixed. The nice thing now, if we have something like this where instructions are shuffled all over the place, if we manage to properly put all the chunks belonging to the same function or the parent, then if we switch to graph view, we don't have to navigate all over the place like we do in a regular listing. So here if I switch to graph view by pressing space, I can see the whole thing in one go. And this is the complete function with all the three chunks. Remember, Y0da did not find all the three chunks correctly. And we'll see this problem in the call function here. So we have start. It's made up of 4 basic blocks. And they're simply stitched together with those jumps. One instruction, one jump, every block is somewhere else. So I'm gonna click on each block and keep an eye on this arrow here. So the first block sits here, second block went here, and so on. And it's gonna be the case throughout this whole challenge. So this is an indication of instruction shuffling. We'll see maybe later in the future we have instances where we have basic block shuffling, where more than just one instruction gets shuffled. We'll have a whole block dislocated and joined by jumps. Now that we manually fixed one function at the entry point start, and we revealed one subsequent function that we need to follow. So let's see now. So this is really not useful. Even if I press tab to decompile, there's not much. So let's follow this first called function and eventually see how this challenge works. So let's follow this one. And now, same story. We have one instruction, jumps, one instruction, jumps, and keeps on jumping. Eventually it will return. Same story. Let's press spacebar to see if Y0da managed to capture all of the chunks correctly. And here Y0da did not know how to continue. So it should have really followed all the way to the return and so on. Same story. Let's follow this second call as well. So let's take a look at this one. Here Y0da detected not many chunks, but we'll see that it has thousands of chunks. And now it's clear that every instruction might have its own chunk, since every instruction is broken and moved So let's follow this one. So first spacebar on this one as well, just to get a quick idea. We have the beginning correct. It started to follow a bit correctly, and eventually it gave up, doesn't know how to continue. So let's go back here. Actually, let's just show you as we go here how it continues, and it continues, and it will continue forever. Really, it's a big function. So how do we approach that with Y0da? If we are to do this by hand, I showed you how to do it. So all we have to do is simply find the missing part and making part of that chunk. So anytime Y0da misses, we simply select the missing chunk, edit, and then function, append function tail, and add it to the parent function we think it belongs to. Now, Y0da is not good with doing those chunks automatically. It's not necessarily designed for this kind of lightweight obfuscation, I would say. So I'm gonna turn off the function tail creation automatically and instead employ a script I wrote just for that purpose. The goal of that script would be to find all the chunks and make them belong to the same function. Like this, if we follow the function and press spacebar or decompile, the whole function should be visible to us in the decompiler or graph view. So I go to the options, general, analysis, kernel options, and here we have delete function tails, which is enabled by default in the configuration in Y0da CFG. We can also go to Y0da CFG, analysis flags, and turn off that bit. I turn off that bit. I'm gonna go back to start and delete that function and start over. So now I'm gonna run a script I wrote that has that logic to follow those instructions and stitch everything together. Before showing you the source code of the script and passing, we're not gonna go in details right now. I'm gonna run it. You will see the side effects, and we're gonna discuss a bit how it works. So I'm gonna run the script here. I call it ATI. It might change the name when I release it. So let's just run it and let's see the output here. What do we have? So here what we're looking at is the output of that function and how it detected all the blocks automatically. It did some optimization on the chunks and finally applied the function chunk creation. So the first step of the algorithm is unrelated to Y0da. It simply asks Y0da to give it the instructions or the bytes. The script will disassemble things on its own, build a data structure, and then finally invoke Y0da to apply all those stuff that we detected. So I just simply run that script, press spacebar, or even decompile, and it has it correctly. So we can do the same for this function here. I can also run the script. Here by default, Y0da, as we said, aborted, didn't find everything. So let me rerun the script at this function here. And now we found 8 chunks in total. So that's even better. Pressing spacebar, we have all the blocks all the way to the return, and along the way we see another call. I'm gonna do that one more time. I'm gonna follow this call and also run the script. Let me clear the screen here and rerun that stitching script and let it run. Now this is a big function, and here we discovered 2456 chunks. So as I told you, it's gonna be massive, and this is the overview. This is the graph overview. It's a big function here, and if we want, we can hit the decompiler as well, and we can see the initial decompilation of that function. Let's invoke the decompiler by pressing tab and see the end result. It might take some time because it's a chunked function and so on, but when it's over, we will have the initial decompilation with no obstacles. So really the first challenge we got, and as we will see applied throughout this whole CTF binary, is that we have instruction shuffling. So we're gonna apply that script recursively. Right now I'm running it one by one, but if we run it recursively, then I can get the whole program stitched up and fixed in Y0da. Therefore, we can nicely disassemble or decompile without this inconvenience. The advantage of stitching things together is we get to create a function in Y0da, and when we create a function in Y0da, we get to track the stack variables, the arguments, and also we will be able to decompile, most importantly. So why waste time in the assembly if we don't have to? So here it is, out of the box. We have already, we can see here the Yoda logo, but we didn't see it when we run it yet. So we will see as well how the code emits that and when and so on. We already see some stuff revealing, some DLL names, some functions, and here from here on it's gonna be a matter of cleaning up the decompilation and simply renaming functions and documenting the whole process. Now that we know what is the function of this stitching script, let me quickly walk you through the source code. And as I said, later on we'll go into details. The gist of that reconstruction or restitching script is to just discover the instructions and connect all the jumps and emit the list of linked blocks, because now since we have one instruction and then a jump, it is considered that the basic block is really just two instructions. So really we're collecting basic blocks even though the basic block is a single instruction. So I have some helper methods to check if it's called and so on. That will help me build the basic blocks. So basically we're re-implementing basic block construction because Y0da is failing at that. So this is the gist of the function, and it's a simple recursive algorithm where we start with the function start and then we follow it recursively, and as we explore more blocks we continue adding them to the exploration stack. And our stopping condition would be jumps we can't resolve, indirect jumps, and return instructions. So this algorithm is simple enough and it works as intended. It builds the chunks, and at the end we run a basic merging just to optimize overlapping chunks. And finally, this is where we apply this into Y0da. And what we do in Y0da, we delete the previous function and then start over again, creating a new function and creating the chunks. So it boils down to creating a function and append function tail programmatically for every chunk that we discover. That's it. So this is the stitching. Now I applied this throughout the whole binary and generated a cleaned version of this program where instead of having the blocks kept at different location and stitched, I have cleaned as well and joined them to be close to each other using another script that will rewrite the instructions. So after I discover all the chunks that are all over the place, every chunk goes somewhere else. It's just navigating all over the place. I added one more script, which is a combination of instruction relocation and copying and so on. At the end of the day, it will copy this to a new section called new, and that's where I will be moving all the instructions. I'm using keystone and capstone as a way to copy and relocate instructions. Now that's the only framework I'm using, so I'm still within the bounds of really using minimal frameworks and sticking mostly with Y0da. So here I relocate the instructions and then I start to copy them and move them around. So there are a bunch of scripts as well, the copying and how we copy, how we fix the relocations. This is a topic we can delve into in details later on in the future. So now what I'm going to show you is the cleaned up database where every function from start has been recursively relocated to a new segment that I called new, and I located that segment just to be one more segment here, as I'll show you in the cleaned up database. And that section will be a total replacement for this text section which contains the instruction shuffling, and the new section here we will see I got rid of the instruction shuffling and built the basic blocks better. So just to quickly to recap, we could have stuck with the instructions being all over the place and only used the stitching script. Instead I wanted something much cleaner, so not only I took all the shuffled basic blocks, I optimized them and relocated them to be locally next to each other. So now I'm gonna open the cleanup script and stop using this shuffled binary. So one more thing I would like to draw your attention to is this is the clean database, and this is the new segment where it contains everything new, no relocations anymore. So if I go to the relocated start, which is equivalent to the originally obfuscated start, that's the obfuscated start all over the place, and the relocated start is really in one piece since we cleaned things up. And we'll notice that all the other functions that I reverse engineered are relocated and cleaned. There's no more instruction shuffling. Then what I did, I wanted to run this clean binary so I can debug it cleanly without any inconveniences. So then I dumped this new section to a binary file, to a bin file. Let's see here. So I wrote a small snippet, very simple, takes that segment contents and gets everything in that segment and writes it to a bin file. Then what I did, I took that binary file which contains the new cleaned code. This is the cleaned code, and I used PEBear from HasherZ, and I used it to create a new section in the obfuscated binary. And then I pointed the entry point to a new location. So all I did really is add a new section. I picked the new section that I want to add, and this contains all the stitched up code, clean code. So I simply load that. We can call it whatever. I kept the name new. I gave it read execute, and then Not only that, I had to also go to the optional headers and find the entry point and patch it to be cleaner entry point, which is this location. So I put the RVA and saved the binary again, and I generated a cleaner executable. If we take a look at that clean executable at a first glance, it is runnable. We can run it, and we don't really use the text, so the text is gonna still be messy, but the actual CTF now is all clean and nice, all in blue, and that's where the whole logic of the CTF lies, and we're gonna analyze that part. So now I will stop that obfuscated binary and I can safely run the clean binary, and that's the clean binary. No jumping around, very clear. And now the problem boils down to a simple reverse engineering exercise. Since we have the decompiler, we can read everything along the way and recover the totality of the source code. Alright, so now let's look at the clean and fully documented database. So let's start from the cleaned entry point. So tab, and here we have the entry point, then calls main, which calls actual main. So what do we have here? They're setting up a bunch of DLL names, compspec, we'll see how it's used, and system, so a bunch of strings. Now here's the trick. So this is nice. The decompiler gave us this nice rendering, but in reality, this is made up of many instructions. Let's press tab and show you what I mean. So that string WS32 is formulated one character at a time. That means there is no .data string that we are using to copy that string to the stack variable. So instead, we're copying into that stack variable, which is a simple buffer, one letter at a time. And that alone will increase the size of the binary. And then you take the instruction shuffling and really you have so many basic blocks. Same story for this string as well, and also for the Yoda message, which is massive. We'll see the whole Yoda message being formulated like that. But why do we care, since now everything is stitched? We have the convenience of the decompiler. When the challenge runs, the first action it does is load WS232, and that explains that listening part. So there is a networking component to it. It loads user 32, verifies the libraries are loaded, and then it allocates a structure. And I call that structure work T, just like a working structure. And throughout the reverse engineering challenge, I recovered the totality of that structure and all the members. I will see how this work structure is used throughout the challenge. So they allocate the work structure, then they put an initial seed value into the seed field of that work structure, and that we will see the relevance of that random seed here. I call it random seed because it's used to see the random generator. So let's press tab, show you a bit. The seed value here is 10D4 hex. And they put it in the work structures as seed field. And then they allocate a bunch of buffers. They allocate a user buffer, and they allocate a buffer for pipes. We'll see where it's going to be used. Allocate what I call the Yoda response buffer as well. It's just one page. And each time it fails, by the way, we will see they're going to call cleanup and exit. Now, there are a bit of details I want to show you. If you're doing this on your own, you will not necessarily see directly virtual unlock. So let's talk about one more obstacle we have in the way and how we solved it. What you see here is virtual unlock calls and other API calls down the line, but in reality, this is not the way it really looks at the assembly level. So I'm gonna press tab and show you. So here behind the scenes, it's not virtual unlock, but I use the decompiler facilities to make it render and decompile as virtual unlock. In reality, it's gonna be using a function called resolve or call by hash, which takes in R15 a D word, which is the API hash that we wanna call. And we'll notice we have so many APIs that will be used and the hashes that correspond to those APIs. I'll show you how I computed all of those hashes in a second. So quickly taking a look at that function here, we can see that it's gonna get the PEB. Eventually it's gonna parse the PEB LDR data, loaded modules, enumerate the modules, and then it will get the image base of every module, parse it as if it's dealing with manually walking the export table. It's gonna go over every symbol in the export table and hash and compare for the hash. So eventually, after it finishes parsing the PEB and all the loaded modules, one by one, get the image base, go to the DOS header of that, go to the data directory. The first data directory is the export directory. It's gonna walk through the names, compute the hashes of the names, and finally it will compare if this is the desired hash. If it's the desired hash, eventually this API is designed to either resolve or call. So depending on R14, to either simply return the pointer to the API or jump to it and pass the arguments. And so this is a classic PEB/export directory resolution. This is really something we can see in shellcode or PE files that have no imports, or they want to avoid going through the regular route of API resolution. So if I open the imports window, you can see that it has no imports. So this is not something we should be worried about. As we reverse engineer, we will see what are the functions that are called, and it's going to be the same for us. With respect to the API hashes, let me show you the hashes I built. So these are all the API hashes that we will be see that are used. Now, how did I build this hash? All I did is simply go back to this function, which, as we said, uses the PEB and follows it to enumerate all the loaded modules. And then for every module, it will find the names in the export directory and does the hashing. So there are two-part hashing in this function. It hashes the DLL name, and also it hashes the API name, and then compares the hash. If this is the desired hash, eventually it will decide either to call the function depending on R14, so it will simply jump to the function that it resolved, or simply return the function pointer. And what I did is simply lift that hashing routine. Now, some of you that work with malware and so on might resort to pre-computed online databases or some plugins and so on. But since here I'm trying to teach you the first principles, I'm not using any third party. Instead, I'm computing the hashes by hand. So the elements of that hash is those transformations, both on the API name and the DLL name. Lifting it is very simple. So is the rotation, etc. So this is the whole hashing. And at the end, it will give us the result. So here I hash the API. It's the hash of the DLL name and the hash of the function. Then I plug that hashing routine with a simple enumeration of the exports, and I get all the names. For every name, I simply call the hash method and build the table. The end result is a simple pre-computed list of all the hashes for every name. Then we can emit this in a header file, parse it into Y0da, and then bring it in as an enum. So when we follow this, this is the enum. One more trick that you might encounter is there's a bit of oddities with respect to the stack pointer tracking. Whenever this API is called, Y0da by default will not properly adjust the stack. So the stack pointer delta is D80, but then as we approach this function here, Y0da will mess the tracking. It will no longer revert back to D08. So I had to fix for this one. All I had to do is simply go to the function and change stack pointer. And every time I had a call to that function which has the similar pattern, set R14, R15 call and add RSP20 and pop, I added that change to tell Y0da to adjust the stack pointer delta. This is very important, so Y0da knows how to track the variables correctly. Then once I have the proper variable tracking, the names will be correct, because if I didn't fix, so if I don't have a balanced stack pointer tracking, the variables will be wrong names. So we'll think, why is it accessing variable 1, not variable 2? And that will reflect in the decompilation. So if the stack pointer tracking is incorrect, your decompiler output is incorrect, and so is your disassembler output. So this is very important to know that the stack pointer has deviated, where it has deviated, and how to fix it, simply by going to the function and adjusting it so that when the side effect of function call, or when the function call is finished, we should have back the same balanced stack pointer as we started. So if I go to the top of the function, here we have the allocation, and it's fixed at D08, the stack pointer tracking. Anytime it deviates, we have a problem. And so it was easy to spot when I enabled the stack pointer here, display the stack pointer. I could see the anomaly that it's not always balanced, and you might see that the first time you see this call, by default Y0da will probably keep it unbalanced, and so what you'd see is not D08. It's gonna keep on deviating each time you have a call, and you'll have different variable names that are incorrectly displayed in Y0da just because of the tracking being incorrect. So I fixed the stack pointer tracking, and I also changed the way this is decompiled, as I said, using the other and decompile as. Like this, in my decompiler output, I no longer see this function. Instead, I see cleanly what is being called. And I've done that throughout the whole program. So that's the second obstacle we observe. API calls are obfuscated, and there's a small trick to fix the stack pointer tracking. Okay, so let's summarize so far. Instruction shuffling, obfuscated API calls through API hashing. We had to lift the hashing and then compute the hashes, and also we had to change the stack pointer tracking. Now back to it over here. Let's continue analyzing the actual logic of the program and see if there are any more obstacles. So now that they have allocated a bunch of stuff, put all the pointers needed into the work structure. So we have a bunch of buffers, buffer for pipe read as you see, Yoda response. They clear the Yoda response, fill it with 0, and as well some of the things you'll notice, as I said in the non-cleaned version, that what we'll be dealing with is just unnamed functions. This is the same function. This here is exactly the same function that we cleaned up. If I put them side by side, see the result is much better. So between here and what I have here, this is the cleanest we can get. So here, for example, checking the 2 pointers, this and this, and so on. Much cleaner. As you notice, I'm like almost having the source code. So let's continue. And now we start to see some actual logic. So the first thing is the regular windsock initialization, WSA startup. And then also we have a bunch of pipes. So every time I create a pipe, we'll have to specify both ends of the pipe. And so here's a create a pipe, put the 2 ends of the pipe, the read end and the write end, into those fields in the work structure. We'll see how those handles to the pipes are linked into that whole challenge. Another pipe as well is being created and another set of input and output ends for the pipe. And then we have a socket creation. So now we're getting somewhere. And then we have the bind. As usual, remember, this is not what you really see in actual disassembly. So what we see here, all of those and so on. Stack pointer tracking has been cleaned. Everything is clean and so on. That's why we have this nice readability here. The port, is in reverse order, so HTONS. And so this one in reality is 0539, which gives us the actual port that this challenge is waiting on. So now we know what port we should be connecting to. But let's analyze a bit further and see what we can do, how we can connect and start working with that challenge. Second step here, there's a function call. That function as well was obfuscated with instruction shuffling and so on. But after I cleaned it up by stitching everything together, just run the decompiler. Same story. Every API call you see, by the way, again, is going to be of that form. Every string you see in this challenge also is formulated one character at a time. So if we look at this, so we have just a string, and we have as well here the decompiler continued building the script using this mechanism. It's readable enough. We get the gist of it. Let's delete those orphan comments. And what it does, this function, all it does really is simply use write console, which also was obfuscated, to display that message. As simple as that. So display Mandiant logo is the function that is responsible for displaying this at startup. So like this, we know we are on the right track. After the logo has been displayed, then it's gonna enter the listening. So this is gonna block until a client connects. Once a client connects, we accept that connection, we have the client socket, and then the challenge continues. It will clear the compspec buffer and some environment variable, and what it will do is simply get the compspec environment variable. What's the compspec? It's the path to the command interpreter. So that's the compspec here. This is really, since the DOS days, it used to point to command.com, and that environment variable, we can get it just to get the command line interpreter. So they get compspec, and they also get the system root, which we said as well is being initialized as such. And also, if we inspect this, see it's going to be pointing to Windows. So we'll see why they want to resolve compspec and Windows. Finally, they employ the same resolution. So here a new API. I called it new because it's the new copy. So I have 2 copies. I have the API get create process, which is in the obfuscated part here up here. And I have every new function. By default, my script simply copies the same functions and gives them the prefix new. And the resolution, so this one will call the resolve like we've seen, but this time it's going to call into R14 the value 1. Which, if we take a look again at the prototype of that resolution which we covered earlier, it's not a regular function. It's a user call prototype Why user call? Because it has a non-conventional calling convention. So I had to specify explicitly what are the inputs and outputs. So that function will return something into RAX. That would be if we decide to call or not call the function. So if don't call, basically controlled by R14, is passed. So if you say don't call, then the return value is the pointer of the function we're resolving. And if we want to call, then the return will be the return of the actual called API into RAX. So this function receives the API hash and the whether to call and not call, and the rest are basically the regular calling convention. The way we, as I said, render this nicely in Y0da is through the decompile as, and that will basically give us whenever it's relevant. So I only apply the decompile as at the actual call site. Alright. After they resolve the create process API pointer and create thread, they check if no null pointer, and then they remember, so something here before they call the create process, they're gonna invoke the compspec, so they're gonna run cmd.exe. But one important thing is a very common thing when we call create process, we have to pass a startup infrastructure, and we have a chance to redirect the std input, std error, and output. So here we see the redirection to the pipes that have been created. We'll see this mechanism is simply to create a remote shell. We're gonna run compspec, and every time the process wants to output something, it's going to output to the pipe. There will be a thread waiting to read the output of the command.exe, and then the challenge will simply take input from the user, pass it through the sockets, and so on and so on. So this is, as we see, it's like a remote shell implemented in this CTF. So once they create the process with the std in and out and error redirected, we will not see anything. So when this program runs, this is the parent of the command prompt, and command prompt is not going to show any output. We're not going to see the output because they're going to go to the pipes. So they create the process, and if they succeed, then they're going to also call the send method. They're going to send a message to the socket, to the client that connected. And here there's a small loop that will send over the network a string. And we see this is really just a basic loop to send over the wire all the remaining message that we want to send. And this number is the length of the Yoda message, which is a big string. So the Yoda message here, this is the whole thing, and they're sending it through the wire. So the user connects, we will greet the user with the Yoda message, and then we will have two threads being created. One I called pipe reader thread, and one I called the serving thread. And if we fail to create the threads, we exit, and then we wait for the process that we created to terminate, and then the challenge returns. So now what will be happening is here is gonna wait for a connection. A client will connect to the 1337 port, the elite port, and then the output of the command will be transferred over the socket, and we will be interacting with cmd.exe through the sockets. For that, I'm gonna be using the netcat command. Instead of me writing my own client, why not just simply use netcat? So I'm just gonna use WSL and an Ubuntu installation. It does have the netcat. I could have equally got Windows version of netcat. I don't want to do that. I just simply want to directly use something on my system. So here I'm gonna say netcat localhost at that port. And look what happens now. I connected, the client here has been unblocked at the listening phase, so the accept happened, and then we displayed the greeting message, and now those two threads are gonna be working, and the main thread is blocked, and so now there will be two threads, and we'll see it's gonna be serving to receive the output from the client and also serve the output back to the client, and some logic in between. So now we have to continue that challenge. We have nothing more to do in main. We have to now explore both threads and see what comes next. So now what we're dealing with is the parent of cmd.exe, and this will be what we deal with. And here, look at this. We have command output. If I simply say, for example, any command is gonna work equally. So now let's go to the threads and explain what happens. Remember that we have a clean executable that we can attach. So in reality, anytime I need to have some dynamic analysis, I have a clean binary that is runnable. So I can simply run. And at one point, I wanna run it to show you more tricks and obstacles in this challenge. So let's take a look at the pipe read thread. So what happens here? Also, I did my best to clean up the decompiler output, and there's no challenges here except the ones I mentioned, cleaning up the stack and applying API hashes and so on. So all those stuff we have already explained. Everything has been cleaned up. We should be in a good position to understand what that first thread does. So it does resolve peak named pipe to see if anything has been written to the pipe, and they also want to reserve the read file. Then we see here that they're putting the JPEG header. So these are known constants. We'll see why they want to have those constants set up. There should be a check somewhere, and we'll see why and how. Then we see as well a formulation of a message that says master Yoda says, and they allocate some buffer in that thread. Then they also check if the resolution for those two APIs succeeds. Then they loop indefinitely until it fails to get anything from the pipe. Then after that, it will read from the pipe. Remember that pipe has been hooked to the STD in and out of command. So this will read whatever the command prompt has outputted. We'll see then there's some check here into a field of the Yoda code work struct that has been set up. So if we go back here, this Yoda code has been allocated in somewhere. We'll see where exactly. So if that pointer is set, which we don't know yet where it's set, then there'll be some logic. And we'll look at that logic at one point. But if that buffer is not set, all this does is simply send back the output from the command.exe back to the client. So that's why here we see back the output, just because of that reader thread. And now in that reader thread as well, there seems to be a loop variable, which is initialized here. And that loop variable is also used to decide whether to enter into this if statement here. So not just we need to have the Yoda code set up, not only we have the Yoda code point beginning with the JPEG header, so they're doing a mem compare. They also will only do this logic after it goes through there's lots of bytes on the pipe. So like every time it reads, and so on, every time the loop counter will increase and we will get an output. So this is also something that we will see, like why we're not getting something as an output. It all depends on that loop variable. So we want to see now where this Yoda code gets initialized and how we can enter this logic here and what's happening here. So we'll get back to that, but for now, this is the totality of the pipe reader thread. Waits for command.exe's pipe to have something for us. We will read from the pipe and then send it back to the client. Therefore, anytime we do a command here, it's gonna be as well. This here will be sending to the other thread, and when CMD has an output, it will send it back to us. Remember here we are connected via sockets, so this is really nothing but just like a terminal. It doesn't have any logic except what the logic is in the challenge itself. Now let's go back to the other thread. So I'm gonna go back to main and follow the other thread. So the serving thread, let's take a look at this thread here. So this thread will receive the input from CMD and do something with it. We enter that thread and let's see. This thread as well, same story. It will formulate a bunch of strings. Same story. Those strings are formulated one character at a time. If I press tab, we'll see the same thing. I didn't spend time pressing R here to reveal them as characters. There's no need. I'm mainly working in the decompiler. Set up two strings. We'll see what those two strings are, but they do look promising. Like give me secret, give me advice. Okay, so let's see what happens. They resolve write file, check if it's there. We'll see why they need write files. Then they allocate some buffer. I called it receive buffer, where they have 4000 hex. And then they clear a receive buffer, a user input, which is in the work struct. And now they wait from the client to send something. So here we're waiting for netcat client to send something. So we're gonna wait for the netcat client to send us something. When it sends us something, then we're gonna copy from the local buffer to the work structure as much, and then we're gonna clean up the received buffer. We're gonna get rid of the new line characters. We're gonna remove the \r. We're gonna remove the \n, and as well those individual functions I had to reverse them to give them proper names. So you will not necessarily see those names. You will enter that function, you look at it. I did rename everything here, and they're small functions, so you can immediately deduce what we're talking about, like we're replacing characters and so on. And then so we said we're waiting for input from the netcat client. So once the input is received and we clean some characters, we compare the input with the advice string. Give me advice. If the user enters give me advice, so if the user says that, then we enter another function called give me advice. It takes the work structure with all the variables we initialize and so on. And the work structure includes the socket, the buffers we allocated, the random seed, and so on. And it's being passed a variable here, the tip number. We see where that comes into play in the output. And let's follow that function here. So let's see what's inside give me advice. Inside give me advice, same story. We have a lot of strings formulated one character at a time, but after I cleaned the disassembly, I recovered 12 messages. Those are different advices, I would say, and they are fun. They're written in Yoda's language, so the English is Yoda English, and they're supposed to give us some hints and so on. Some of them are kind of like taunting, for example. Obfuscation leads to anger, etc., etc. Some stuff about the decompiler. Let's see, it's tell us to drop our decompiler and so on. Yeah. Train yourself, let go of your decompiler, use your knowledge, like try to be smart, etc. Really, those are fun, but we have the source code. This is just for fun, nothing else. Then they also formulate a message, and here we have format specifier %x, and we'll see that it's gonna be the tip number that I mentioned in the caller. Then they allocate some buffer as well, obfuscated API call, nothing special. And then they allocate 12 pointers, and they're gonna copy all those local buffers to those messages array. And here is important, very important. We see it as well later as we continue. So again, I access the seed. So the initial seed we started with was here, that one. And we see later that this seed is gonna be changing. So they take the seed from the work struct into a local variable. For some reason, if that seed is 0, they reseed it with another magic constant. So between this one and this one. But again, that seed will see the full purpose of that seed. Then they format that message, and we should see the Yoda life tips and the tip, and also the number of the tip and the message. And so they use the tip that we passed here from the caller as a seed or a pseudo random index. So they take the tip number, they add to it the seed here, modulo 12, because of the message table length. They increase the tip number. So like this, they kind of, every time we ask, give me advice, is gonna pick one of those messages here. And then after it pick one of those messages, it will make the network loop to simply send the whole of the message. So we say, give me advice. What we will see is a derivative of the seed that's used. So we get the internal view of what the seed might look like, and then a message back to us. So now if we go back to the serving thread and enter give me advice, it should go and output one of those tips, and then it will, because we typed this was supposed to go to command, so give me advice should have went to command.exe. Instead, they replaced the things that were supposed to be given back to command's std input handle. They write a new line. So when we type that command, instead of being passed to cmd.exe, it gets swallowed. They send back a response through the socket. We see some tip, and what cmd.exe receives is just a new line. It's like as if we typed enter. So we will not get a command error. So let's test it out real quick. I'm gonna copy that, go here and type give me advice. This will be intercepted before it's sent back to CMD's std input, and we'll get one of the random tips. So let's see here, and we got here, this is the initial seed, that's the magic value, and we got no try not or etc. This is one of those hints. Let's try again, and now we have something else. Now the seed has not changed. We'll see who will modify the seed. So far the seed is read only. So in the give me advice, one more time, nobody is writing to the seed as of now in the give me advice. So the seed which influenced the tip number is not changed. So it's just read and used for the influencing of the tip number that we see on the screen. We'll see how that will be handy if we want to compute the flag with no debuggers, no nothing. If we are simply given the output of that string and some other outputs, we can offline compute the flag for the user. But again, that's one approach. Let's continue. So this is give me advice. Nothing really useful. You can ask give me advice all you want. I would say the most useful thing is just the revelation of the internal seed value. But that text is just for fun, but it's not gonna help us any further. But we have other secret commands. So if it's not one of the secret commands, so if it's not one of those give me secret or give me advice, it's gonna take whatever the user typed and pass it back to the command.exe's std input. So that's why when I type something, then it is sent to CMD. CMD will execute it. It will write to its pipe. The reader's thread will take it and send it back to us, and we see it. But only for secret commands, they're gonna be swallowed and replaced by a new line. So like this, we don't get a command error. So here, if I type give me advice, but it wasn't swallowed and sent as a new line, it's gonna be directly sent to CMD, and we should get like an invalid command. So that's how we are adding secret commands on top of cmd.exe. Now let's talk about give me secret. So what happens in give me secret? The moment we type give me secret, then another message is formulated on the stack as well, one character at a time. This is gonna bloat everything and also serves as a deterrent against the strings utility. We won't see it directly, and I haven't tried to even use floss. Again, I'm trying to avoid using any third party as much as possible and keep it to the first principles and using Y0da. Again, if you're using lots of frameworks and so on, now if you're experienced, you know what you're doing, that's great. But if you're the beginners, and it's good to know the basics so you don't rely on black box tools and so on. So let's follow the give me secret. We formulate two messages. To know the secret you want, you have to give me a password, and also they formulate the wrong password message. Then they allocate some buffer. Let's expand this, and they send back to the client a message which is the give me password. So once we say give me secret, we will get please enter give me a password to send it to the client, and then still wait for the client, for the netcat client, to type something. Once it receives something, it cleans those return spaces and \n, and then invokes check password. So first, let us go to the client and type give me secret. And here, to know the secret, give me the password, and it's waiting. And it's exactly this one here, give me the password, and then it's waiting on the receive. So now let's talk about how the password is verified and what can we type in the password. So check passwords takes the password stripped from spaces and so on, and the work structure, let's follow it. And here we go again. I cleaned this up as well. This is just a matter of working with the decompiler, cleaning things up and fixing the stuff I mentioned earlier. Now, first thing is as well, they again want to check for the JPEG buffer. And now they call check pass with the password that user input. So let's follow that function as well. You have to clean that function and so on and so on. Here we go, it's cleaned up. So I cleaned up that function, and what I noticed is they are formulating a bunch of 16-byte hashes, and we'll see this is gonna be MD5 hashes. And so we have 4 different hashes, and I call them hash part. We'll see why. Then we have the full password hash as well, and then as well there's a character delimiter here, and we'll see how it's gonna be used. So if the user didn't pass any password, the password check will fail. It will display a wrong pass. So let's go through the wrong password first. So let's put something here. Here we go. We got the no, this is not the right password. So let's go back to give me secret and see how we can go through the check password and get a successful password. So check hashes. So we have 4 parts, 4 individual hashes, and 1 full password hash. Now, how did I name those and why? We'll see in the following logic. So the first thing is they take the length of the password and they put it in that allocated buffer. Also, you have to reverse engineer this as well. So this used to be a dummy function. As well, you could have used crypto identification functions and so on. Since this is clean, you should be able to run external tools if you want. But when I was looking at it, these were all dummy functions. I entered this dummy function and I immediately recognized those. And so it's a direct MD5 C implementation. Very clean, very straightforward implementation. And as well, I didn't want to go into the details. It was enough for me to just rename them on a higher level and see what's happening. And it was clear to me it was computing the MD5 and returning hash. So they take the full password and they hash the full password into the password hash variable. And then they do a check. They compare the MD5 hash of what we typed against the full password hash. So it now boils down to, can we find a string that's MD5 hash will be this one? Of course, now that is possible, but also it could be challenging. If it's a string, if the string was complicated, it might not be in a rainbow table or pre-computed MD5 table that we can use. So brute forcing will be really tough. We cannot really brute force this. So what we want is, given a hash, give me the input. That's tough. So the CTF writer knows about this and helped us. So the first thing is here, full hash. At first glance, it's impossible to know what's the full hash. So since we cannot just necessarily brute force the hash, and I tried. So let me show you. I went online and I searched for MD5 rainbow table, and there is a famous website that you can use like CrackStation, for example. And over here, all I did is simply tried to put the full hash, and I didn't find the results. So I have the full hash, and I said, let me try my luck. Maybe if I'm lucky, I can find a string that hashes to this, and that should be the password. So when I say, okay, let's try if that pre-computed MD5 hashes, or actually this will have pre-computed bunch of different hashing algorithms. And I said calculate, and this hash was too complicated to guess what is the input for it. But that was not the end. So then I looked at the code and saw that they tokenize with underscore the password. So the password has underscores. And what they did, they made a small loop and they initialized the part index with 0. And they made a loop, they tokenized, and what they want is apparently the password is delimited by underscore. So there be part1 underscore, part2 underscore, part3 underscore. And in the loop, for every token, so this is token 1, they compare against, so they tokenize it. That means if I had something like this, part1 underscore, part2 underscore, 3, part4, then they're checking part1 against the hash part1. And then they checking part 2. Of course, the underscore is part of the token is gotten rid of. So we are looking for what is this part 1 that will compute to this hash. What's part 2 that compares to this hash, and so on and so on. And what we're looking at now is individual parts. So now we have the full. So let's say this one is full pass is made of 4 parts. And we have 4 hashes, or say 1 full hash. Then we have 4 individual hashes. And so now if we can recover smaller parts, so maybe it's easier to calculate if we can find some input that gives us hash part 1. So I simply went and copied that hash into the actual representation like 4C84, and I put it in that calculator here and say, okay, this is the first part. Maybe this is a less complicated string. Maybe we'll find a collision. So let's try. And I was lucky. It's meant to happen. I mean, otherwise, how can we guess unless there are other pointers? So that's the first part. And I did the same for each part. So I put here the second part, crack it, and I got U. And eventually, all the 4 parts are patience. You must have also in the Yoda English style. So I put all of those together using underscores and typed it as a password. So if we go back to the Netcat client here, and it's still waiting for a password, we're gonna put the whole parts underscore wise, and if we combine the parts with underscores and compute the whole part hash, we should get the full pass as well. So what happens is all the parts will pass, the full hash will also pass, and that function will return that all the parts are okay and the full hash is okay, then the password is right. When the password is right, we're gonna continue and see what happens next, which is like the get Yoda code and so on. So patience, you must have. And look at this. So we didn't get a wrong message. Instead, this is the right password. We got something like Master Yoda says and some cryptic string, which we will see how this is formulated. So we're really getting close to the end of the challenge. So once the password succeeds, we're gonna continue further down the line. Now, since nobody set the Yoda code buffer anywhere in the code we've explored so far, that if will enter and then call get Yoda code. That's a function, that's what I called it. And it receives an output variable code size. So let's see what happens inside this function after you put the right password. So you put the right password, we follow it. And here we have 2 strings, Yoda and master, and then they call get image base. They use the obfuscated APIs. So these are the obfuscated APIs to go to the resources and find the resource and master Yoda directory there and load that resource and simply return that resource. That's all it's doing. So if we have a resource viewing tool, we can extract the same buffer from the resources from the binary. I can show you this in the resource viewer. For example, I have resource hacker and I drag and drop this executable, and this is the resources that they're trying to retrieve. Going back to Y0da, that function really all it does is simply retrieve that resources. And I called it Yoda code. Now For now, it doesn't show as Yoda code yet because after they retrieve it from the resources, then they call RC4 decrypt with the password we put. So the password we specified is vital for the decryption of that embedded resource. Once that resource is decrypted, then that's the first time they check if it's a JPEG. So that resource, although here doesn't have the JPEG header yet, once it's RC4 decrypted, it will. And here, if I show you the JPEG, that's what we get. The flag you have not found, and also it says at a glare on, not FlareOn. Fine, so I put the correct password and we still didn't get the flag. So what's going on? What's the next step? So check password, all it did is then check the correct password and decrypt into the Yoda code work field. So here we have a Yoda code. That Yoda code is the RC4 decryption of the embedded resource, and it was decrypted because of the correct password. So that's all it does. So give me secret, checks the password, internally it will decrypt into Yoda code. And it displays the message that it got, and that's it. It's not gonna say no or anything, but it simply populated Yoda code. Okay, so what happens next? We gave a secret and we decrypted Yoda code, and that thread is just back in the loop. So once we put the Yoda code, we got this. How did we see this output? Remember in the other thread, we said it is referring to Yoda code, but we don't know yet why. So we're back to that thread here where it's simply reading and sending the output back to the client. And we have this I loop counter. Now that Yoda code is gonna be set because we put the correct password. So this points to the JPEG. Then this secondary thread as well not only checks that the Yoda code has been initialized, it also makes sure one more time if it's a JPEG, and also check if this is the right time to act upon that. So let me show you, for example, here if I just press enter a couple times, I start to see this message being repeated automatically. So here, just enter, and it's changing, by the way, and we're gonna explain how and why Yoda says something else. So now, even though I'm not typing any password or anything, just because I'm interacting with the command.exe, it's gonna go through this reader worker thread and gonna check whatever the user types in the client, reads it, and if the Yoda code is set, which we set, so every time now we loop 3 times, it's gonna execute that code and display a different Yoda response. What's the Yoda response? Here, Yoda says. But why is it changing? So the Yoda says is changing each time. And we have string concatenate to the Yoda says message. So it's gonna display Yoda says and the Yoda response, which is that buffer. So we need to know why is it changing and how is it computed. But now we know if I just press enter a couple times or keep pressing, when enough read happens and the loop gets increased, then we get a chance to see more messages. So like this is keep on changing. And if we say give me advice, it will show us the seed internally. And that seed goes hand in hand with this encoded output. So here, if I say give me advice, this is the seed, which is going to change, and we'll see how and why. But if I press enter again, okay, now it changed. And we have the seed here. That seed we can use to decode that. So if we are supporting someone remotely, say, okay, you're running the challenge, let's help you get the flag. We say type give me advice, give me the tip number, and also give me the encode, what Yoda says. And then using the tip and using this, we can decrypt the flag. And we will also continue delving in that logic and see how everything fits together. So I'm gonna go back to the reader thread, and now we're gonna see what happens each time that loop happens, and it's gonna display something, what's happening. It's gonna enter this code path. So let's explore that code path. At this point, I'm gonna attach a debugger and explain a few things. I have set up my process options correctly. I just have to simply attach and pick the right process and the right process. And that's the executable I wanna attach to. So what we can do now is go back and maybe put a breakpoint. We can wait for it here, for example, and we will see what's happening. So now that we're attached, if I press enter a couple times, it's gonna break here and we can start tracing. So let's first resume the process because I attached and I didn't resume. So okay, now it's resumed. Now it broke, and now we are dynamically tracing this. So this is the nice advantage of me taking the time to stitch back everything and also connect them next to each other and emit a clean binary. So by doing that, I saved so much time down the line because now I'm dealing with the regular reverse engineering problem without all the obstacles in the way. So now let's see what's inside decode via ROP and actually why I called it decode via ROP. So ROP, return oriented programming. So Yoda buffer, which is a picture, let's see it as well in memory. Where is it? It's in W. which is the work struct, if we apply work T, and the Yoda code is here, and that's the JPEG. So that's exactly the JPEG that I just showed you. So let's go back to the code and trace into the decode via ROP. Before I stay inside the disassembly view, I can just continue a bit here in the decompiler. Now, the reason I can't fully continue in the decompiler next, just because of the nature of the code. So it's always good to have a good balance between decompilation and disassembly, especially when we're dealing with obfuscated programs or irregular programs. Decompiler might not be well suited to deal with unusual code. So we'll responsibly use the decompiler and the disassembly as needed. So again, they formulate the JPEG header as well. They want to check that they're dealing with the right thing. So they check if the Yoda code has been set. And as we said, it's set if you type into the give me secret the proper password that computes to the right hashes. Then they compare again that the Yoda code has been properly RC4 decrypted and it has JPEG header. Then they allocate a couple memory pages. They allocate memory buffer 1 and they allocate another buffer. I called it random memory. We see because it's going to be initialized with some random stuff. And then they allocate as well one more. I called it memory pattern 1 with that len. We'll see why I call it like this. And they're gonna also allocate one more buffer. So in reality, they're allocating all those buffers for now and see how they're gonna be used. Then they will clean all those buffers they just allocated. And I also reverse engineered this function, and this was simply a pattern matching function. It matches 4 bytes. So I notice here they're doing pattern matching into Yoda code JPEG. They're scanning for the whole JPEG for pattern 1. And pattern 1 has been initialized like that, FFE1AA3B. So if I go to the Yoda bin and let's search for that pattern, okay, and let's type FFE1 AA3B. Now, why am I using Hue, not Y0da? It's the same. I could have used Y0da as well because I'm already debugging. I have the decrypted view and so on. So, but if I were statically doing this analysis with you, I wouldn't be able to see the pattern in Y0da. But if I was, I'll show it to you as well in Y0da. But let's say here. So it's actually from the buffer. It's going to be at around that area here. So if I want to still show it to you, we can, let's see, where are we? So here we are at the work struct. Let's follow it. So if I go back to the Yoda code and go here, advanced, this is the 4 bytes for the pattern. And here we have 7F2B, etc., etc. And that is towards the end of the JPEG. So here we're almost done at the JPEG. So towards the end, let me mark it. So let's go here +4 and let's just mark a bit. This is 39 hex. There's another pattern, but there are 2 patterns in the JPEG. They're looking for this pattern with the special pattern beginning indicator. And there's another pattern as well continuing towards the end. And as we'll see, that pattern, the secondary pattern, wherever they find it, we're looking at a bunch of ROP gadgets. We have operation return, etc. So we have around 500 gadgets as well, and we'll see how that will be used. Going back to the decompilation, let's wait for it here at the pattern matching finding. And so here, after they find the pattern as well, we can find it. So that's where they found the pattern indicator. They're gonna skip past pattern indicator and grab that buffer here, and that will be the flag. Encrypted or encoded flag. So they find pattern 1. If they find it, they skip 4 bytes and they move it to that buffer. So here 39 hex is the pattern. I think I have those patterns. So I have mem39. This is the flag I extracted from the JPEG. This is the encoded flag exactly in the JPEG. And the second one, I called it ROP, is the, I will show you what I mean. Let's wait. So the second one as well. So here they find the second pattern with the second pattern value, and they capture it into mem gadgets. So now this one I can call mempat1 is encoded flag, for example. So that's the encoded flag. They find both the flag, and here we have the sizes. So I have the size of the gadgets, 451 or 1C3 hex, and the size of the flag, 39 hex. Then they have the SRAN to start setting a new seed with the seed from the work structure. So they get a seed, and then they have additional buffers here on the stack. And as well, I realize they're using this algorithm here, Mersenne, Twister. It's a pseudo-random generator, and all the constants I've seen checks. So what they're doing, they are taking the seed from the work structure and then using it to seed the Mersenne generator to generate into the random memory, which is allocated earlier. So they're calculating a buffer using a predetermined seed. And so that buffer will just contain random. They're not really random because once we have the seed, we can reconstruct that buffer. And so since the seed comes from the work struct, we know what's the random generator. We know what's the seed from give me advice. We can always reconstruct random memory offline. So we say give me advice, we get the tip number, we seed it through srand and empty genbuff and generate number, and we generate the random buffer. That random buffer has a specific length. And now this is where the magic happens. So after they calculate the random mem, they call a function I called ROP unscramble. They use this function to unscramble the flag given its size, and they pass to that ROP unscramble method also the random buffer, and also they give it the gadgets which we said are inside the end of the JPEG. So in that method we're gonna see how the flag is dealt with. So if I follow ROP unscramble, so let's see how does this work. But before we go into that method here, so here let's press tab and show it to you in the assembly. So the ROP unscramble so far looks okay. It initializes some variable like this, it has the I that we see, and then for every character in the input, apparently what we don't know is they are simply invoking what I called execute ROP chain. Then continue. They're gonna do this for the whole input. They're gonna call execute ROP chain. Let's see what's inside this one. And that's gonna be really interesting and the last part of our discussion. So let me put a breakpoint here, let it run and step a bit. So that function, let me decompile it. Look at this, I decompiled it, I don't get anything useful. And that means let's take a look at the disassembly. So once I switch to disassembly, I notice that they are receiving R9 from the caller and they are moving it to SI and they're adding to SI some displacement. Then they push it. Then they take back R9, they add some offset into it, they push it. So here they're pushing offsets. What are those offsets? If we take a look at R9, if we go back to the caller, R9 is the gadget buffer, code buffer or gadget. Here in this assembly I call it code buff, we can call it gadget code buff. So R9 is receiving the gadgets and we can see it here. So if I go to R9, this is the first gadget, this is the second gadget, and remember these gadgets are coming from the JPEG. So, and again, really quick, here the JPEG. Towards the end, if I switch to decompiler and switch to 64-bit, these are all the gadgets here we see. And so the execute ROP function is pushing all the ROP gadgets, and then eventually after it pushes all those, I'm gonna quickly reveal that if I say user defined offset to R9, it will reveal the gadget in question. So here it's gonna show me, well, you're gonna be using this gadget. Let's press Ctrl R, and then you're gonna be using this gadget. They push all those gadgets, I think around 500 of them. And so these are simply displacements into the gadget code from the decrypted JPEG. And after they push all of those, as you can see, so let me go to the end. And then after they push all those offsets, eventually the first gadget they're gonna execute. So here they're gonna say return, and return will start the ROP chain. Return until it exhausts all those things, eventually returning back to the caller and repeating the whole process for the next character. Few things I would like to mention, very important things. As we enter this assembly function, so execute ROP really is an assembly function. You can see here at the start of the function, it is using the frame pointer and the stack frame of the caller. So in reality, this one will have access to the local variables here. And we'll see how we can use that to our advantage in a second. So I wait for it at the end. Let's run to cursor here, or F4. And now we start the ROP chain. So if I press F9, I'm gonna go to the gadget code in the debug segment. And that's the first ROP chain. This RBP plus 24 is in reality accessing something in the stack frame of the caller. So here, for example, I'll show you what that is basically the index that exactly resolves to the caller of this one. If we open the stack frame of ROP unscramble and scroll a bit, we'll see that the ROP chain has access to that stack frame of the caller, which is the ROP unscramble. So it will have access to the index, and exactly the gadget we were looking at is accessing the index I, and so on. But I'm gonna show you a cool trick in a second. So this is the first chain. It's gonna do what it needs to do and then continue the next chain and the next chain. And this is not sustainable for me. I cannot reason about this nicely. So I'm gonna show you a trick how I can have something more readable of the ROP chain. So I'm gonna convert a ROP chain to a function, and let me show you how I did that. In order for me to convert the ROP chain into something more readable, what I'm gonna do, since I traced a bit into a couple of ROP gadgets in front of you, I'm gonna redo it. So I just have to, I wanna run my code snippet that I'm gonna explain, but from this point onwards. So here I'm going to put the breakpoint and just simply re-trigger that whole process by pressing enter one more time. It will go through the I loop modulo 3 and it will execute again. So we're gonna wait at first invocation of the ROP chain at the first letter in that encoded CTF buffer. So let's just press enter. It so happened now it was picked up quickly, like that I loop happened to be okay, so it entered that. And what I want is to capture it just before the chain starts. So when we go to the ROP unscramble, execute ROP chain, I wanted to catch it here. So let's run. And here, if I go manually to the stack pointer and dereference it, we can see now the return. If we let it take place, here we'll have all the chains. This is what have been pushed, and all of those really are pointers. So these are the subsequent ROP chains. So one chain will execute something, then return, it returns, will continue here, execute the second chain, and so on, and so on, and so on. So the script I wrote here, what we have is a very simple stack walking loop. I dereference the stack pointer, and my stop condition is if we eventually return back to away from the gadget memory block back to the code that we were using. So this is my stop condition, that no more ROP chains. And then each time I dereference the stack pointer to get the chain, I decode it, and maybe the chain is composed of multiple instructions before a return. I keep decoding it, but if I find a return, I simulate stack pointer advancement to advance to the next chain and the next chain and so on until it breaks. Breaks meaning breaks out of walking the chains. And then I accumulate all the code of the sequence of gadgets in the proper order into a stream of instructions. So it's no longer a ROP chain, it's simply a stream of instructions. So let it run, and these are the instructions, like here, these are the sequence of instructions. Then what I did, I simply dumped the code I collected into a binary file. Once I dumped it to a binary file, I disassembled it with Y0da, so I had a simple ROP binary, which is the proper order of the gadgets. So these are all the individual gadgets that would have executed if we let it run in a gadget manner, like return, 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 return. But instead, I, let's say, flattened it or made it like a sequential execution instead of a series of returns. When I did that, now it's a matter of simply loading this in Y0da, and as I told you, that function has access to the same stack layout of the caller. So if we go to the execute ROP chain, when it enters, it inherits the frame pointer and the stack layout of the caller. So we should have access from the ROP chain to gadget code, random buffer, ROP size, ROP data, I, and some local variable, which I'm going to talk about in a second. Then I took it on the side here, and that's the whole ROP chain. Now it's a bit more reasonable that we have a series of instructions. Now again, I'm not gonna look at it like this. Let me give a shot to the decompiler. But before I do that, I wanted to give it the proper prototype. So since this function enters with RBP frame pointer of the caller initialized, I reconstructed what the layout would look like. So here I have some gap, that's fine. I have something here I call temp. We see that temp coincides with this guy here. This temp here, I can call it a decoded character. So that coincides with that variable. Let's open the stack window here. So this one maps here. Then we have 3 bytes gap. So we have +3 takes us to I, which is the index. Then we have gap, 24 bytes gap. Then we have access to the buffer pointer. We have some gap. We have access to the random buffer, which is generated using a known seed and so on. By mapping that structure, I could decompile and reveal the logic on a higher level. So what I see here is I call that structure data, and what they're doing is initializing into that variable. They're reading from the buffer, which the buffer here is really the input. So, and at the index I. So this exec ROP chain is this code here. So that's the ROP chain. This is the decompilation of the ROP chain. And now we can see how that logic is hidden behind that. So here what they're doing, they take the buffer, which is encrypted at the first index, or whatever the index is, and they do a series of transformations. And they do those, all of those in function of the index and the buffer at the index. That's it. So they keep on doing that at XOR, etc., all the way, until we notice here there is some kind of a logical split, I would say. There is now a shift in logic. We see something different now. After they computed this here, now something else is taking place. And that decoded character, or this temp, is only in function of the buffer at the index and just the series of constant XORing and basic arithmetic. So it's not in function of the random buffer, and the gadget code now is out of the question. This is the gadget code. So really, the first part in that logic, in the ROP logic, only uses the index and the input at that index. So that's the first part of the logic. And then the logic here shifts to now access the random buffer. Now they're taking the random buffer that has been initialized using the random seed. And then what they're doing is they're simply using that random buffer. They use the same index, I, and they simply access that index into the random buffer. And they XOR all the bunch of indices with the computations they did prior here. And then they write it back to the buffer. So they decoded a single character and then they encoded it using this formula using the random buffer. And then they return back the buffer re-encoded. So if you want to think about it, this part of the logic decodes one letter at a time of the flag. This logic here re-encodes it in function of a random factor, random buffer basically, which is in function of the random seed. And that's the logic of it. So what happens is after the ROP unscramble executes, the input buffer, the flag that's encoded, is decrypted and then re-encoded again in function of the random buffer. So in reality, if we want the flag, we want to intercept it before it's re-encoded. But I'm going to explain the re-encoding part, and I'm going to explain how we can leak out that part without having to deal with this part here to decode it again. So all I want really is just that variable here. And I told you, since this variable is never touched again and never encoded again, it leaked out here as a decoded character. So every time we call the ROP chain, the decoded character maps, in that point of view, maps to this variable. We can call it here decoded flag character. That decoded flag character is accessible to us outside the ROP gadget. So I don't have to go through the gadget anymore. All I have to do is simply, every time the ROP chain executes, I have to wait for it and grab decoded character because it's going to be affected and changed from the ROP chain. And if you notice in the disassembly, if I cross-reference on that variable, it's only being initialized, and one might wonder why we have that local variable and why nobody's writing to it one more time and nobody's reading it. In reality, this has been written to multiple times and even read multiple times. So that same decoded character is read and written to multiple times. So what I'm going to do is I'm going to simply put a breakpoint here, let the first iteration, so I is 0, let it finish once, and we're going to inspect the decoded character. So here we are at the start of the chain. I don't need that anymore. It's going to continue executing every single chain. That's fine. But it will return to the caller, and it came back here. After it came back here, if we look at the decoded character, I have a single character here called P. Let's make a byte P. All right, so that's one character. But the actual input buffer, it's re-encoded again using that encoding, or I would say scrambled. So let's say it's scrambled again. Let it run one more time. Let's give it one more iteration. Now that's the second iteration. I is 1. Let's go to the decoded character. So now what I'm going to do, gonna put the cursor here at the decoded character and simply open a watch window and watch that variable here. So let's put it here, for example. So now I have 0. Okay, let's run it again. It breaks again. Now I have W, for example. And I is 2 now. Let's also watch I. So let's go to the debugger and add watch for I as well. So now I have I. Now we can give them a name here. Let's call it I. And this one, let's call it decoded flag character. Just a single character. And I have W. So P0W so far. And let's press F9 again. Now 3, R, F, U, etc. So what I did, I used conditional breakpoints. I put a conditional breakpoint at the entry of that ROP unscramble, which will be called in a loop. But before the loop enters, I simply put a conditional breakpoint that creates a global variable that is of type string into the global scope. and I initialize the flag string with an empty string. And that breakpoint does not cause a break because I return 0. And then at each loop, I added another conditional breakpoint, and you guessed it, I simply grab the character and add it to the string. So all I do here, simply again declare that this is the global variable we introduced in the previous breakpoint condition, and add to the string, just dereference the stack value, the decoded character. I hard-coded the offset with respect to the stack pointer, which is okay. I converted to a character, added to the string. And finally, I added one last conditional breakpoint to display the flag at the end of that decryption routine. So now if I let it run, let's create a screen here, let it run, because of those conditional breakpoints, it will accumulate every single character automatically for me and display it to me here. So let it run and look at this. Powerful, you have become my young FlareOn at FlareOn. So that's the flag, but we're not done yet. Some of you will have a different approach, and I will continue explaining the totality of the CTF. So I think this is a very good approach, because now we demystify ROP execution and we could logically see what's happening. And we have two approaches to deal with that. Let me show you one of the approaches I took, that I can do this offline. So what I did here is, since I decompiled that ROP chain and I have the data buffer, which is the encrypted flag, so that flag we captured from the JPEG, which is located using a pattern. So we find a pattern, we find that flag. This is the flag decoding algorithm. So what I did is simply lift it, simply copy the decompilation, copy the structure, etc., and run it. Run this. Like, I don't really care about the details. So here I have the flag, and this is the flag I encoded like that, and I call decrypt flag. What's decrypt flag? That's decrypt flag. It's simply the copy from the decompiler. I just cleaned it up. I got rid of the data structure since I don't need it. So I don't really need to go through ROP work structure. I just need the decoded character and the buffer and an index. The index is going to be inside the function. So all I care about is the buffer and its size and the output here. So I simply make my own loop and do the same. I just copied pasted the whole thing, and that will decrypt the flag for me and it shows it to me. So people can have two approaches. One is like that, and the other is through, let's now continue and see what we're dealing with over here. That's what we can also leverage. Between grabbing the seed, we'll see how the seed will affect the encoding, and then we can do the reverse process. So eventually, if we're gonna take another approach, we're gonna take that and we're gonna see how this string is formulated, and then do the reverse of this operation. So we're gonna take that, decode it. It's not base 64, it's base 32 with a special encoding table, but we're gonna decode it to get back the raw buffer like that. And we're gonna do the reverse operation. So we're gonna build the random buffer using the seed from give me advice somewhere here. We're gonna use the Mersenne twister with the seed that we derive from here to generate the random buffer. I'm gonna do the reverse algorithm to decode. So we're gonna base 32 decode this to get the binary, and the reverse operation should give us back the flag. So now let me show you back in the clean database. So this will re-encode the buffer. So here, ROP unscramble. At one part, it will decode the flag one character at a time, but as the flag character is decoded, it's immediately encoding using a pseudo-random buffer. Once it's re-encoded, then they call base 32 encode. Now again, you have to reverse this and understand how it works. I just traced it a bit and figured out that it does look like a simple encoding algorithm. And I just managed to see the table. So the encoding table as well, you can grab it from here. Okay, I did as well re-implement it. So here, this is the encoding. So it's not like say A, B, C, D or 0. The encoding characters are different. So even if you have vanilla base 32 encoding, you have to shuffle the table that's used for the encoding. And then if I say base 32 decode this string, and you will recognize this string OIZ, this is the first output we get from the first time before the seed rotates. I haven't showed you yet how the seed rotates, but I'll show you. So if I scroll to the first time I input the password, and you will see it. So let's see, where is it? Here this OI, this is the first time before the seed rotates. So every time the seed rotates, the re-encoding will be different because the random buffer used to re-encode is different, so we get different encoding. But I didn't take that approach. I didn't want to deal with this. I simply copied the ROP gadgets all the way up to that point I showed you, and that's it. So back to this one, we base encode into the Yoda response, and then when this finishes, we concatenate to the message, and the message was master Yoda says. We add to it the response, which is the encoded base 32 encoded output, and that's what we see here. Now I haven't shown you the seed rotation, but every time we'll have the same thing. The flag will be temporarily decoded then re-encoded randomly, and the output we see is base 32 encoding. Now we display the results, stream the response, and then let's see here, seed. Okay, so seeding next happens immediately at decode via ROP. When we find the patterns, every time the srand will change. When I call srand, give it the work structures, the seed, it will update it for me. So every time we go through the decode via ROP, each time now the seed is gonna change, and that explains how the seed is changing. And so I think this is it. There's nothing more here. We got everything we need. Let's see, go back, and we're going back to main. So nothing else to see here. So it was really fun doing this challenge. I hope actually you learned a lot, because we covered a bunch of tricks. We also explored how to convert ROP into logical code. We discussed about sharing the frame in the ROP gadgets and the caller, and we learned how to stitch instructions back together conceptually. Of course, we can go in details, reapproach this, and go into the details of stitching and relocating instructions. I know this has been a long video, but I did my best to explain high level detail and explain the full logic of that CTF. I hope you enjoyed it, and I'll see you next time. Thank you.